Okay, so to pick up the thread of the story, we saw the idea of an execution of machines in the UC model last week, this sort of intricate dance between external machines, internal machines, the adversary and the environment, and how we orchestrated interaction between all of these parties to model some kind of cryptographic protocol that is being executed. And today I'm going to give you some real, genuine definitions of what these objects are. And the goal is that we're going to see how we can state some theorems about them and prove some results. We're not going to prove anything terribly fascinating today, but we are going to see how the definitions really work out. Okay, so I'm going to start with the interactive Turing machine. And I am going to assume that you kind of already know what a usual Turing machine is, otherwise we'd be here all day. So, for our purposes, an interactive Turing machine I'm going to call this an ITM because we're going to use this word a lot, or this phrase. Call it mu. It's a Turing machine with some extra stuff. With, this should not be terribly surprising what I'm going to add to this. We discussed several different communication tapes, so these are obviously going to get in there. The first thing that I add is an identity tape that, surprisingly enough, identifies the Turing machine. This is going to be, it's going to contain the ID number, and it's also going to contain the definition of the Turing machine itself. And we're going to need that eventually. We want to be able to specify sending messages based on properties rather than ID numbers. So it contains mu's identity, which is, if you recall, it's some tag, perhaps if you like a natural number, plus an encoding of the transition function, just considered as a normal Turing machine transition function. Use whatever encoding you like. I'm not going to be pedantic about the details of that. And also the initial tape contents. So enough information to define what the Turing machine is. Okay, so that's the identity tape. We have an outgoing message tape. This is going to act as a buffer when the machine wants to write a message to another machine. It's got, yeah, that will have a message. It will probably start empty in practice, but it'll at some point contain a message N and some kind of routing instructions, as in where is this being sent to and how. I'm not going to write out a specific model of this, so there's nothing especially complicated. You could, again, choose whatever encoding you like for these details. And we have externally writable tapes, so this is where the machine is going to receive input. And they have particular properties that they're read-only, so the mu cannot write to it, any of these, and they're also read once. So when the machine reads a message, the tape advances and it can't be rewound. And this is simply because we're modeling receiving a message, right? You receive a message, the message disappears into the ether after you receive it. Okay, so we have, these are the ones that we... Sorry?
Nothing to stop the machine. There's nothing to stop the machine writing it to a work tape while it's reading it and then copying
Right,
it.
exactly. It could copy it into some kind of working... It could copy it into the main tape, if you like, and work with it there if it wants. But to simplify the communication model, yeah, we're going to say that these tapes are special. So it's an input tape. There's an input tape. This is when the machine is called as a subroutine. There's a subroutine output tape when it returns data, or when it has data returned to it.
Who can see the identity tape?
Yes, the machine, a priori, only the machine itself can see the identity tape. We'll see as we define an execution where this goes. So the idea is somehow some mysterious, some force living in the ether can see the identity tape, so it knows where to send messages to. We'll see how that works when we formally define the execution.
I guess I don't understand. I understand why it contains the identity from the discussion last time, but why should it contain a code for mu for some UTM? What's the point?
Yes, this is a natural question. Basically, this is because in some cases we want to. So what we're going to build up to ultimately when we define improved composition is we want to be able to swap out pieces of machines. We want to be able to replace a part of a protocol with, say, let we assume that we have a uniformly random key, right? We might want to replace that with a pseudo-random generator operating on a smaller piece of material, and the composition theorem is going to say that we maintain security when both pieces are secure. And because of that, the machine, it may not even be one machine, or the identity might change when we do this substitution. So we want to be able to somehow define a predicate of machines that we send messages to. And of course, there could be other ways to capture this as well. But the UC model is defined in really quite strong generality to allow machines to simply say, I'm going to send my message to the machine that has this operation somehow.
Okie doke.
I probably would not have defined it this way if I were to define it, but this is how the model is defined. So the other thing was the backdoor tape. And I just write a little reminder to us, this is for adversarial behavior. So if a machine is leaking data to the environment, or maybe it's waiting for instructions from the adversary, this is all going to go through the backdoor tape. Okay, another thing it has is a single bit that says whether the machine is currently active. So active means that the machine is computing something according to its transition function, and then when it sends a message, it will become inactive. So we have a tape that stores whether this is the case. We have another read-only tape that is a randomness tape. If you read the paper that I'm sourcing this from, it doesn't actually include a randomness tape explicitly, but I feel that we probably should because we're going to need it later. So it's a read-only and read-once randomness tape. You can think of it as a stream of bits that are drawn from some distribution. We're gonna treat it like it's uniformly random, because you can always do randomness extraction on a non-uniform source. And it's going to be long enough somehow because there is no uniform distribution on infinite binary sequences. So we just hand wave and say, let's just make it long enough that the machine will never actually run out of randomness in practice. Okay, so those are the extra tapes that it has, and the machine also has extra instructions. So it doesn't just have read, write, move the head. It has a couple more instructions. So the first thing it has is external write. It can write to other machines' tapes. And I'm going to define this later on because it's quite complicated, and I'm running out of space as well. The last thing it can do is read the next message. So from these externally writable tapes, it can read a message. So normally, like a priori, the Turing machine can only read from like one specific, from its tape that it normally has. So we're going to say that it's got an instruction, and you specify which tape you're reading from. So it's T in input. I'm just going to write output because subroutine output takes forever to write. So specify which tape you're reading from, and what it does is it jumps to the end or to the start of the next message. On that tape. And the way that this is going to be implemented is we require that all messages are delimited by, so they end in an end of message symbol. And that way the instruction simply says, okay, I'm going to read the tape until I encounter this symbol, and now I'm ready to continue reading. Basically, this is going to, what we might have is we might have messages of non-constant or even potentially unbounded length, so the machine needs a way to skip all of this extra data that maybe it hasn't consumed. So these are the pieces of what our interactive Turing machine is. Do we have any questions, perhaps that aren't about this extended identity? Which I forgot to define. So all of this stuff is called the extended identity, because it's the identity of the machine plus all of this extra code, if you want to think of it as code.
Mm-hmm. No, I think.
Yep. This is somehow what one might expect. I move on to the next board. Okay, so this is where I diverge slightly from the UC paper. The UC paper makes a very confusing distinction between interactive Turing machines and interactive Turing instances, which is not really necessary for the theory. My impression is that this has crept in through, the paper's gone through like a dozen plus revisions over the last 20 years now, I think. So my impression is that this is sort of some extra machinery that has crept in over time. Okay, so I'm going to define another few key terms so that we can just discuss things efficiently. So a configuration of some ITM U is it contains basically all of the data of the tapes and the machine. Contents of all tapes, the location of the tape head, heads plural, and the current state of the Turing machine. Okay, it is, we say it's active if the activation tape contains 1.
I find some of this a bit confusing. Can the Turing machine write to its own activation tape? Can it read from it? And if not, then it's not really a tape. It's like some property of the machine that. Like
yes, I think this is a I think that's a sensible criticism. This could probably be rolled into some other part of the protocol rather than thinking of it as a tape. I would agree with that, yeah.
Or just a configuration, right?
Right, sure, yeah. The way it's done is that when I define the external write system, when I define the external write instruction, this will control the tapes somehow. But I agree with you that this doesn't necessarily need to be a tape of the machine.
But it probably doesn't matter either way, so...
It doesn't really matter, I think, yeah. So we'll define an activation of an ITM, of course. And this is going to be a sequence of configurations. And I cannot write of configurations of mu. And an activation has to start in an active configuration. And ending when we reach an inactive one at the first inactive one. So an activation it's a sequence of tape contents, tape heads, and Turing machine states, and it has to start when the machine becomes active, and it has to stop as soon as it becomes inactive. Somehow I think this is a sensible thing to define. Okay. Now we define a system of ITMs, or an ITM system. And there is I apologize for the terminology overload. This is kind of just all dumped at once, and this is sort of necessary pieces. But the way that I think you should look at this is these are fairly intuitive ideas. We're just doing our bookkeeping and making sure that everyone knows what we're talking about when we say such things. So it's a pair of machines of a machine I. I should probably write this as mu to keep consistent. We'll see why it's called I in a minute. You see, where C is a control function. So the idea of the control function, which I'm not going to define formally just yet, we'll come back to that, is it controls which machines can talk to which. So last seminar we discussed communication sets. Perhaps not every machine can talk to the adversary. Some machines accept external input. Some machines talk internally. The control function is going to abstract this idea of a communication set, and it's going to say, whenever I write externally, I'm going to ask the control function, am I allowed to do this right, yes or no? The control function is going to say yes or no, depending on whether the write is allowed by the rules of the execution. And it's also going to potentially, in some cases, replace some values. So when we want to send a value to a subroutine that we later swap out with some other construction in the theory, the control function is just going to do the bookkeeping to make sure that it stays consistent, because otherwise an environment could trivially distinguish a substituted subroutine by looking at the transcript. So it's going to this control function is going to ensure consistency and potentially edit some data.
Sorry, I feel like I'm entering a Kafka novel a little bit.
Yes, can you go on?
When you say whether you have permission to write, isn't that specified by the protocol, which was this graph-like thing, or am I misremembering last time? So
yes.
So an ITM system is, but it's not a protocol is not part of this data, right? So the control function is like something you could derive from a protocol, but is more general than a protocol.
So the control function, we are going to define a control function, one control function that we will use.
Okay.
Now that I think about it, maybe it makes more sense to somehow just have this one control function, but the theory is built to potentially allow different control functions. I guess the idea is to allow variants of the UC theory, depending on modeling details. but we're going to only work with one fixed function, and that's going to be defined together with the execution of a protocol with an environment. Does that help?
Yeah, then I'm not so nervous. Yeah, that's great. Thanks.
We will fix a specific one. So, it's sort of a question of how much generality you need, not completely clear. The basic idea of the control function is it says where the messages are allowed, and it potentially can redirect messages to allow swapping out things, subroutines with others later on. Okay, so with this terminology, I'm now going to define an execution of a system, not of a protocol in an environment yet, but of an ITM system. Okay, and this is going to be another big definition, so I'm going to go to the other board so that we can leave it up as we go. Okay, so an execution of a system. I'm going to call the machine I now because it acts as an initial machine, and it will potentially spin up other machines as it goes. And an execution has to be given some input, call it Z. And an execution is a sequence of activations. So recall a configuration is the state of a machine, and an activation is a sequence of configurations. Now we're going to consider a sequence of activations. Potentially different machines are going to take over at each element in our sequence of activations. And for it to make any sense, it has to start with the initial machine, which I call I. Okay, so we're going to define the external write instruction. Remember, we have this external write, and now with the light of what an execution is going to be, we just have one machine to start up. Now we need to think about, okay, if I only have one machine in the beginning, obviously at some point I'm going to have to start running more machines. The initial machine at the end of the day is going to be the environment that starts up the protocol, that starts up the adversary. So now we need to define the external write instruction that I did do before.
Sorry, Eleanor, the orb got stuck halfway to this board. Could you just trot a little bit over here and hopefully it'll get unstuck? That should be far enough here. Just stop moving and it should... Okay. There we go. Okay, sorry about that.
No worries. Okay, so the picture that you have in your head, you start with one machine, and then it can start up new machines, and then once several machines have started up, they can interact with each other, and that's how we get this sequence of interactions. So the external write instruction is the key of this dance. Now, I apologize for the jumping back and forth. The paper is written this way. I tried to synthesize it a bit, but this is maybe a first attempt at synthesizing it. Maybe I can condense it further at some point in the future.
Okay, just so to make sure I'm passing this right. So an activation is itself a series of configurations of the Turing machine.
It says, yes.
So you've got now a sequence of activations.
Yes, because the initial machine starts up, it might create some more machines and then pass control to them.
Yeah, okay, cool.
So the subsequent activations will be of different machines, even though in the beginning there's only one. Okay. We interpret, again, using some encoding that we don't necessarily specify. So we interpret the outgoing message tape as a tuple with the following bits in it. It's got F, M prime, T, R, M, and little m. And of course, I'm going to define what these are. So F is a flag, it's a bit. And this is called a forced write flag. What this does is it says, if the machine I'm trying to communicate with doesn't exist, should I create it? So the initial machine is going to use the forced write flag to spawn new machines. Later on, you might have machines that say, I want to send a message, but I'm not going to create a new machine to do it. And this is where the control function comes in, right? We don't want the protocol to be starting up new machines left, right, and center. So it's going to tell you whether or not a particular machine is allowed to create new machines. So it's called forced write. This is maybe a confusing name. The idea is simply, when I send this message, if the target doesn't exist, do I create it? Yes or no? Okay. Now M prime is the destination.
What does it mean to create it? Like, you mean add it to some list of active machines, or?
Yes. Yeah. So the theory does not explicitly model, say we have a set of machines maybe we don't have an execution that contains a set of machines and an activation at each step in the sequence. It's just sort of, there is some list of machines floating around in the ether. And the reason it does this is because it's a compression, right? If I look at an execution prefix, so I'm currently running an execution, I look into the past, by examining the activations up to this point, I can determine which machines exist. So it's not modeled explicitly in the theory. Does that make sense?
Yeah, I think I follow you.
Yeah. So whenever I send a message with the forced write flag that says, now a machine that meets these criteria has to exist, and I don't need to explicitly make it a set because I can tell which machines exist by looking at the execution prefix. So
I guess this is probably pointless complaining about this, but I don't understand why even use the language of create then. I mean, you just sort of assume all possible machines exist out there, and then you write to it. No.
Yeah, that's my perspective as well.
Okay, cool.
We'll call the paper. This is where sort of a distinction between interactive Turing machines and interactive Turing machine instances creeps in. So we talk about instantiating machines, but I don't necessarily think it makes sense to do it that way. Anyway. So M prime, the target of the message, is an extended identity. It contains an ID number and some code. T is which tape we are writing to. Input, output, subroutine output, that is, or backdoor. R is a flag that says whether we're going to write our identity onto the tape. So for example, the environment doesn't always reveal its identity when it talks to the protocol. And in particular, machines that belong to the protocol have to reveal their identity. So this is another thing that the control function will examine. Okay. M is the sender's identity. So whoever's executing the external write function instruction is going to put its extended identity into M. And little m is, of course, the message. And it can be arbitrarily long. Okay, so now we have to define exactly what this behavior is. So what the control function does, we can now concretely say that it maps these tuples to each other. So it's going to map, f m prime t r m m to f. I'm just going to draw a bar over the top to say it can change this. And again, we're going to use one specific control function later. So perhaps you might fear this is way too much generality, right? But we're going to restrict it to one specific one that we care about later on. So it either maps it to a tuple like this, or the simple disallow. So the control function either maps the tuple to some new tuple, potentially probably just replacing the target identity, or it says, no, this message is not allowed. This is special simple, sort of a disjoint union of the type of the product, of the type of the tuple and the symbol disallow. So if
I don't really understand. So that signal disallow, where does that exist in this universe? That's on a tape somewhere, or it's
this is just some value that we agree signals disallow. It doesn't exist in a sense. So when we execute an extended write function, we evaluate the control. So when we execute an external write instruction, we evaluate the control function on this tuple and see what the result is. And that will define the further behavior of the external write instruction. So disallowed doesn't exist anywhere in the model. It's a mathematical artifice.
Yeah, I feel like we are a universal Turing machine that's sitting there writing to all these tapes for all these machines or something. And you're saying that if it's not disallowed, then we end up writing something to somebody's tape somewhere. Is that right?
Right, yeah. So if we evaluate the control function and we get disallow, then the initial machine, is activated. So if a machine tries to send a message that it's not allowed to do, we just activate the initial machine again. And what activation is muse activation tape. Is set to 0 and I is set to 1. That's what I mean when I say activated. So if a machine somewhere in this system attempts to send a message and it's not allowed to do it, we say no, and then we give control back to the initial machine. Remember, in practice, the initial machine is the environment. So it essentially says if the machine tries to do something illegal, the environment takes over. This is what I was referring to last time when I said potentially a machine can pause without sending a message. So this is a case where a machine tries to send a message, doesn't, therefore isn't active anymore. Now the environment takes over again.
Does it know that it failed?
That's a good question.
Because couldn't it write to its work tape? Like it just tries sending to a bunch of machines. It writes an encoding of this tuple, then tries, and then writes another one, and then tries.
Right. Well, okay. So it can only try one because the environment is going to take over immediately after it.
Well, it might end up running again for some other reason.
Right. No. Okay. So if I think about this, I would say no. It doesn't know that it failed. To know that it succeeded, it would have to ask the receiver to send an ACK back. The machines are not automatically allowed to evaluate the control function themselves.
Okay, cool.
Okay, so otherwise, if it's not disallow, I go back to the first board because unfortunately I'm running out of definition space. Okay. So we evaluate the control function and it says we're allowed to send this message. There are 3 cases. First of all, if the forced write flag equals 1, which says, remember, I'm going to make sure a machine with this identity exists, and an earlier activation. So recall that we're being activated in the context of an execution. So if in a previous element, a previous activation in the sequence of activations, there's a machine with extended identity M prime. So we're sending a message and the sort of magic universal Turing machine that's orchestrating this says, yes, we can send this message. If there's a machine that already exists, then we do the obvious thing. M, the message, is written to tape T of the receiver M prime. I have a sentence in my notes that I don't understand. Oh, yes. So the machine in a sequence of activations obviously has many different tape states. So obviously when we write to the tape, we mean at the end of its most recent activation, we take that tape state and append our message. Okay, if the reveal identity flag is set to 1, then the sender's identity M is also written to the tape. And after that, of course, M prime is activated. So its activation tape gets set to 1, M's activation tape gets set to 0, and the next step of the execution is M prime's work. Okay, the second case is, I phrased this carefully to avoid writing too much. Otherwise, so we're not in the first case, but we still have the forced write flag. Then we're going to create the machine. So what this means in concrete terms, the next activation in the execution, it'll be the machine M prime. So recall M prime contains the identity and the code. So we've got everything we need to pluck M prime out of the ether. And of course, we set its tapes to the initial content. And we also add the message to its tape. And that will be the same as in step 1, case 1. So we're forced write, the machine we're writing to doesn't exist, or hasn't been activated in this execution. So we're going to pluck it from the ether of surrounding machines in its initial configuration, and also put M at the end of its at the end of the target tape. And we say M prime is invoked. So by invoke, we don't just mean activated, we mean created and then activated. Okay, so now in the other case where we don't have a forced write flag, then we have a slightly sticky situation because M prime may not literally exist, but we can't create one yet. So this is where the model gets a little bit hand-wavy. We interpret M prime as a predicate. And the specific way that we do this is not spelled out at this step. So the idea is that, for example, you might say, okay, give me any machines that have the same code. Maybe they have a different ID number, but they have the same code. So we're looking at all of the machines that have been invoked so far, and in some unspecified manner, we interpret the target machine as a predicate. And we take the ITM, or we take the earliest invoked ITM satisfying M prime and deliver the message. As in 1. And if no such machine exists, if we get no matches, then we treat it as a disallowed communication and the initial machine takes over.
So it seems like I could force a write which creates a machine with the same ID number as an existing machine, but a different code.
Yes, you could do that.
So ID numbers it's the ID number plus the code that is the unique identifier of a machine. And
yes.
Is that actually unique?
Yes, it is. It is unique by definition, because we always say that we have by taking the earliest machine that matches the predicate, there's always a canonical choice. And if we have force write, then we specify the full code, and it is exactly that machine that is invoked. So the extended identity is 100% certainty a unique identifier. I can't recall off the top of my head, but I think we would expect that the control function would not allow you to do something like creating many machines with the same ID number. This would be somehow pathological and excluded by the control function. But in principle, the model can capture this if for some reason you wanted to do that. Okay, so the 3 cases say the first case is force write and the machine exists. The second is force write and the machine doesn't exist. The third case is a non-forced write. Okay.
I don't think I really understand what the forced here is. I mean,
the forced, yeah. So it's saying if the forced write flag is not set and I send a message, the message may not actually go anywhere. If the forced write flag is set, then if M prime doesn't exist, then I create it. So the message is always sent when forced write is set to 1.
Yeah, I get that, but when force write is not set, there's also this predicate matching thing, which is more general than when f equals 1. So it seems like a mix of 2 different behaviors somehow.
Yes. Yeah. Okay. That's a salient. I think that's a decent comment. For the record, aesthetically, this seems a little bit suspect. The way that this is phrased is quite, it's quite vague.
Yeah, I kind of want to make it check to see if the machine halts or something.
Right,
so,
yeah. Well, the good news is these machines definitely halt, as we'll see, probably not today, but at some point.
What guarantees that?
When we define the notion of polynomial timeness for these machines, the condition will require that they eventually halt.
Sure, okay.
Okay, so I'm going to give an example. Yeah.
Maybe you're about to say exactly what I'm about to ask, but could you give an example of this predicate matching business?
The predicate matching business. I don't have one handy. So where we will go with this is we want to model concurrent sessions, right? Because you will recall that the sort of naive model we had breaks down when you have concurrent protocols being played off against each other. So what we'll do is we'll interpret, I might write this down, it's a relevant interpretation of identities. So we will say that an ID, not an extended ID, just a regular old ID, is a pair of a session identifier and a party identifier. So the idea is, of course, you can have many parties participating in a protocol. They will each have different party IDs. And the session ID, when the environment invokes a protocol, it will give an identifier to that session. So the purpose of this predicate business is, what might happen is the environment invokes protocol pi, and then 2 invokes protocol rho. And then what will happen is pi replaces, in some sense that I will eventually make precise, but not yet, part of rho. So for example, rho could be, perhaps part of the protocol rho involves a cipher, right? And then it involves an ideal functionality cipher, right? Something that really truly contains no information about the message that is being sent. But of course that doesn't exist in real life. So we're going to replace it with a protocol pi. So for example, a real cipher. We're going to replace the perfect cipher in rho with a real cipher. And then rho says, I want to encrypt a message. So it says, give me a machine with the ability to encrypt messages. And because the real cipher was invoked first, the predicate will go ahead and find the real cipher. Messages in pi, ask for cipher machine. Fine. Oh, sorry, that should be rho. So the obvious objection here is, okay, well, what is the predicate? And the idea is that it is somehow possible to define a machine that acts like a cipher, in the sense that it can accept messages and then output an encrypted version of, it can output some other message that is correlated in some way, such that when Bob inputs the ciphertext, he gets the message back out. I agree that this is quite dissatisfying.
This freaks me out, I have to say.
Yes.
This just seems like a way of saying that lots of English sentences I say in my papers fit to this standard by shoving all the bad bits into this blue box you've just drawn.
I don't necessarily have an intelligent comment to that, but you were saying?
How do I reason about this?
With difficulty.
I guess maybe it'll become clear, but this seems like a huge black box into which all sorts of things could be put.
Yes. So the ultimate goal here, I'm not going to get anywhere near the end of my notes, but that's okay. The ultimate goal is that we will somehow shave off bits of this model so that it doesn't have all of this incredibly wide-ranging behavior that you describe. This is definitely one of the parts of the UC model that I don't like either. I mean, indeed, we sort of say, the comment about this is a way to stuff all of the English sentences into a black box that somehow magically works out the right thing. When you read papers that use UC, that's essentially exactly what they do. They don't define Turing machines. they sort of, if they acknowledge it, they will say, there is a way to define a Turing machine that does this. And I'm like, okay, I believe you at a human level, but I don't know if I believe you at a mathematical level. The good news is that we can still, with these ingredients, we will eventually, I was going to do it today, but I'm running out of time. We will prove at least first that there is a sense of polynomial timeness that makes sense, which turns out to be not trivial. And the basic reason for this is you could always have machines somehow playing ping pong to bootstrap infinite computational power by talking to each other. If each individual machine is always polynomial time, they can keep activating each other, and somehow you have an interaction that is no longer polynomial time. So we will see a way to prove that you can tame this behavior. Not this week, maybe next week. We did have a slight tangent, but maybe I give an example to wrap things up. I give an example of what this external right interaction is supposed to mediate. This predicate interpretation, I'm honestly just going to say forget this for now.
I guess I'll be happy if later you tell me that I can understand some interesting crypto systems and a fairly general interesting class of things with a very limited use of this, and then I'll
that is the idea. But yeah, I mean it's sort of an aesthetic choice that I maybe would not have made if I was making this model. Okay. So,
could you repeat how the predicate works? It matches against code, does it? Or?
Sorry, what was that?
So with the predicate, does it match against the code, or does it work?
Yeah, it matches against the code in some sense. It's not the idea is if I give you a machine that looks close enough to the machine that you want, the predicate will either say, yes, this is close enough, or no, it's not close enough. So this is sort of what I'm getting at with the example of the real and ideal cipher, right? The predicate is supposed to pick out machines that act close enough to an ideal cipher.
All right. So is the idea of instantiating machines, is that related at all to like dynamically defining subroutines, or do you know what I mean?
Sorry, could you phrase that slightly differently? I didn't quite capture it.
You think of some of these machines as being when you define functions, like inline functions in code, is that sort of analogous, or?
Yeah, it's sort of like let's imagine you have two libraries, right, that export the same API. And the idea is that you should be able to swap one library out for the other. The predicate is essentially saying, does the library that you're giving me match this API that I'm using?
Right.
And if so, it's going to pick out the functions that it needs. That's the picture in your mind, I guess. Okay, so yeah. Go on. Okay, so and I'm going to draw some pictures of what an interaction of this nature looks like, so that we can sort of better understand what this external write instruction does. So, in the first step, we have our initial machine. It receives some input Z, and I'm going to draw the control function as a box to indicate sort of this is our magical escape hatch thing that evaluates the control function for us. And I'm going to draw a green inner thingy to say this is the machine that's active at this step. Okay, so the first thing that happens, the machine receives the input. The input is written on its input tape, and then it's going to read this, and according to its code, its transition function, its states, it's going to maybe write some stuff to its tape, and at some point, it is going to execute an external write instruction. So I'm going to draw this as follows. The universe is going to evaluate our control function. So machine I, it wants to send a message with the forced write flag set. And the target identity is, I'm going to call it mu1. I'm going to call it identity number 1, and its code is going to be mu1. And the tape that we're sending is input. And the reveal sender flag is set to 1. And we also have to give the sender ID. So ID I and machine encode mu I, and we send a message M. Okay, so in our beautiful mathematical universe, the control function is being evaluated on this. And it says yes, by which I mean it outputs the same data, right? It's not outputting disallow. And to keep it simple, I'm going to imagine that the control function doesn't try to do any redirection yet. Okay, so now the control function has said yes. So out of the ether, we pluck machine number 1. I guess I should call it 1 to stay consistent. On the input tape, so I write the word input to indicate it's on the input tape. We write the message M, and because the reveal identity flag is set to 1, we also add the sender ID to the tape. And now machine number 1 is active. Okay, next thing that's going to happen is machine number 1 does some processing. And let's say that it wants to return some data to the initial machine. Again, the control function is going to get invoked by the universe itself, the laws of physics. So no forced write flag. The destination is the initial machine. The tape is going to be output because we're a subroutine of the initial machine. Reveal identity set to yes because we're an internal machine. Those will always reveal their identity when we finish up all these details. It's going to send a message M prime. And of course, the control function says yes, by which I mean it outputs the same thing. And now this value is good.
Why have a distinguished feature called reveal identity when you could just write your ID onto the tape when you write the message?
Yes, the reason is because the control function is going to force certain machines to always reveal their identity. So if it was just encoded at the end of a message, the control function would then have to check that the message ends in the right identity. You could model it that way, but we're doing it via a flag instead. And the idea is that the external write instruction's definition forces it to end up this way if reveal identity is set to 1, and the control function only allows reveal identity set to 1 for certain machines. Does that make sense?
That makes sense. Yeah, I mean, if it was something you got, yeah, okay, I follow that.
Yeah, sort of a lot of the complexity here is realizing when I define an execution, when I define an execution of a protocol in an environment with an adversary, this will specify the control function. And I didn't get to that today, but this will constrain the behavior a lot more. Okay, so 1 is on the output tape, sending the message M prime and revealing its identity. Okay, so we see how roughly how this works. Machines can invoke other machines. We have a control function deciding who can talk to whom and making sure certain rules are followed, like internal machines always revealing their identity and so on. And the execution is built out of many activations, and the way we define this external write instruction for our interactive Turing machine says who gets control when, and therefore defines an execution. Okay, so the important things to take away, I think, are really just the behavior of this external write instruction. And I've written out, what our ITM is going to be. The external write instruction is really the only interesting part of it. And of course, I will post the notes so that you can review these definitions. Cool. Any general questions?
I think I asked all my questions. Yeah. Thanks. That was great. I might sound unhappy or something, but I'm really getting a lot out of this.
This is really where I think the sort of the youth of the field that I was alluding to earlier sort of comes through. I think you have a right to be unhappy because these definitions are definitely not watertight, and there are some criticisms to be made. But my goal is to present the theory as it is, not perhaps the theory as it could be.
Yeah, you've got a PhD to do after all.
That's right, exactly. Okay, can I just leave now? Is there any post setup that I need to do?
Yep, that's all good. Thanks a lot.
Thanks for coming along, guys. Have a good one.
Okay, see ya.
See you next time.
Thanks.